Hello everybody, today we will be talking about RAID disks. RAID, Redundant Array of Independent Disks, is a data storage utilization technology that combines multiple physical disk drive components into one or more logical units for data redundancy, performance improvement, or both. This was in contrast to the previous concept of highly reliable mainframe disk drives, SLEDs. A single large expansive disk. They consist of an array of disks. These disks operate independently. Since many disks are operating independently, multiple input-output requests can be handled in parallel if the data required is on separate disks. A single I/O operation can be handled in parallel if the data required is distributed across multiple disks. The disks in RAID appear as a single disk to the operating system. So, yeah, data is distributed across the drives provided by RAID levels, depending on the required level of redundancy and performance. The different schemas or data distribution layouts are named as RAID, followed by a number, for example, RAID 0 or RAID 1. Each schema or RAID level provides a different balance among the goals: reliability, availability, performance, and capacity. RAID levels greater than RAID 0 protect unrecoverable sector read errors, as well as against failures of whole physical drives. Originally, there were 5 standard levels of RAID, though many variations have evolved, including several nested levels and many non-standard levels. RAID levels and their associated data formats are standardized by Storage Network Industry Association (SNIA) in the Common RAID Disk Drive Format (DDF) standard. There are 7 levels of RAID schemes. RAID 0 is about striping, RAID 1 is data mirroring, RAID 2 is about bit-level striping with Hamming code parity, RAID 3 is about byte-level striping with dedicated parity, RAID 4 is about block-level striping with dedicated parity, RAID 5 is about block-level striping with distributed parity, RAID 6 is about block-level striping with double distributed parity. Okay, let's start with level RAID 1. Level RAID 0. RAID 0 consists of striping but no mirroring or parity. Since there is no parity checking of data, if data in one drive gets corrupted, then all the data would be lost. Data are split up into blocks that get written across all drives in the array by using multiple disks at the same time. The minimum requirement is 2 disks for RAID 0. The advantage of distributing data over disks is that if 2 different I/O requests are pending for 2 different blocks of data, then there is a possibility of requested blocks are on different disks. This offers superior I/O performance. In RAID level 0, logical disk will span all the physical drives. Files are strapped across disks, no redundant information. The capacity of a RAID 0 volume is the sum of the capacities of the drives in the set. The diagram shows 2 drives, drive 1 and drive 2. In drive 1, odd blocks are written, whereas in drive 2, even blocks are written. It works in a way that block 1, block 2, block 3, block 4, block 5, block 6, and block 7, and block 8 will be the order of blocks reading from beginning if it's read sequentially. Advantages of RAID 0. Increases throughput. Throughput is increased because multiple data requests are not on the same disk with high probability. Disks seek in parallel, a set of data is likely to be strapped across multiple disks. The technology is easy to implement. It offers a great performance both in read and write operations. The throughput of reading and write operations to any file is multiplied by the number of drives because reads and writes are done concurrently. There is no overhead caused by parity controls and all storage capacity is used. Disadvantages of RAID 0. It's not fault tolerant because trapping distributes the contents of each file among all drives in the set. The failure of any drive causes the entire RAID 0 volume and all files to be lost. It should not be used for mission-critical systems. Let's move on to another level. Our level is now RAID 1. RAID 1 consists of data mirroring without parity or striping. Data are stored twice by writing them to both data drive or set of data drives and a mirror drive or set of drives. If a drive fails, the controller uses either the data drive or the mirror drive for data recovery and continued operation. Twice as many disks are required to store the same data when compared to RAID 0. Data striping is used as in RAID 0, but each logical strip is mapped to two separate physical drives. Thus, every disk in the error has a mirror disk that contains the same data. Data can be read from either disk, however it is written on both disks. Array continues to operate so long as at least one drive is functioning. Drive 1 is ideal for mission-critical storage, for instance for account systems. It is also suitable for small servers in which only two data drives will be used. As seen on the diagram, we have two disks, disk 1 and disk 2. In disk 1 we have blocks A1, B1, C1, D1, E1, and in disk 2 we have the exact copies of those blocks in disk 1, which are A1, B1, C1, D1, and E1. Advantages of RAID 1. RAID 1 offers excellent read speed and the write speed that is comparable to that of a single drive. On read, it chooses fastest to read. Read performance is 2 times better than a single drive. Drive performance is the same as a single drive. It provides fault tolerance. In case a drive fails, data do not have to be rebuilt. They just have to be copied to the replacement drive. By this, continuous operation is maintained. It's used to store system software such as drivers, operating systems, compilers, etc., and other highly critical files. There is no overhead of storing parity information. Disadvantages of RAID 1. The main disadvantage is that the effective storage capacity is only half of the total drive capacity because all data get written twice. Software RAID 1 solutions do not always allow a hot swap of a failed drive. That means that a failed drive can only be replaced after powering down the computer it is not attached to. For servers that are used simultaneously by many people, this may not be acceptable. Such systems typically use hardware controllers that do not support hot swapping. And now we have level RAID 2. RAID 2 consists of bit level striping with dedicated Hamming code parity. All disks participate in the execution of every I/O operation. Each bit of data word is written to a data disk drive. Each data word has its Hamming code ECC word recorded on the ECC disk. All disk spindle rotation is synchronized and data is strapped such that each sequential bit is on a different drive. Hamming code parity is calculated across corresponding bits and stored on at least one parity data drive. It has a complicated controller, single access at a time, tolerates only one error, but with no performance degradation. Data strapping is used. On read, the ECC code verifies the correct data or corrects single disk errors. In the diagram, we see a byte is divided into 4-bit chunks, and 3 parity bits are added to form a 7-bit word, which is partitioned bit by bit to 7 disks as seen in the diagram. The diagram has 7 disks. In disk 1, we have blocks A0, B0, C0, D0. In disk 2, we have blocks A1, B1, C1, D1. In disk 3, we have blocks A2, B2, C2, D2. In disk 4, we have blocks A3, B3, C3, and D3. In disk 5, we have Hamming code ECC blocks corresponding to the previous disk blocks that are ECCAX, ECCBX, ECCCX, ECCDX, and in disk 6 we have having code ECC block ECCAY, ECCBY, ECCCY, and ECCDY, and in disk 7 we have having code ECC blocks ECCAZ, ECCDZ, ECCCZ, and ECCDZ. Advantages of RAID 2: on-the-fly data error correction. Extremely high data transfer rates are possible. The higher the data transfer rate required, the better the ratio of data disks to ECC disks. Relatively simple controller design compared to RAID level 3, 4, and 5. Disadvantages of RAID 2: very high ratio of ECC disks to data disks with smaller word sizes that are inefficient. Entry-level cost is very high. It requires a very high transfer rate required to justify. Transaction rate is equal to that of a single disk at best with spindle synchronization. No commercial implementation exists. It's not commercially viable. Let's continue with RAID 3. RAID 3 consists of byte-level strapping with dedicated parity. The data block is subdivided, also known as striped, and written on the data disks. RAID level 3 requires a minimum of 3 drives to implement. Stripe parity is generated on write, recorded on the parity disk, and checked on read. Read accesses all data disks. Write accesses all the data disks plus the parity disk. In case of a drive failure, the parity drive is accessed and data is reconstructed from the remaining devices. Once the failed drive is replaced, the missing data can be restored on the new drive. A single parity disk can be used to detect and correct errors. In the diagram here has 4 disks. In disk 1 we have blocks A0, B0, C0, D0. In disk 2 we have blocks A1, B1, C1, D1. In disk 3 we have blocks A2, B2, C2, D2. In disk 4 we have blocks A3, B3, C3, and D3. In disk 5 we have parity blocks AP, which includes A0, A1, A2, A3, BP. And BP block, which includes B0, B1, B2, B3, and we have CP, which includes C0, C1, C2, C3, and DP. At last we have DP, which includes D0, D1, D2, and D3. Advantages of RAID 3: it has very high read data transfer rate. It has very high write data transfer rate. Disk failure has an insignificant impact on throughput. High efficiency means low ratio of ECC parity disks to data disks. Required applications are video production and live streaming, image editing, video editing, press applications, and any application requiring high throughput. Disadvantages of RAID 3: if spindles are synchronized, transaction rate equal to that of a single disk drive at best. Controller design is fairly complex. It's very difficult and resource intensive to do as a software RAID. Another level is RAID 4. RAID 4 consists of block level strapping with dedicated parity, combines level 0 and 3. RAID level 4 requires a minimum of 3 drives to implement. Each entire block is written onto a data disk. Parity for same rank blocks is generated on writes, recorded on the parity disk, and checked on reads. Read accesses all data disks. Write accesses all data disks plus the parity disk. This level was previously used by NetApp, but has now been largely replaced by a proprietary implementations of RAID 4 with 2 parity disks called RAID DP. The main advantage of RAID 4 over RAID 2 and 3 is I/O parallelism. In RAID 2 and 3, a single read I/O operation requires reading the whole group of data drives, while in RAID 4, one I/O read operation does not have to spread across all data drives. As a result, more I/O operations can be executed in parallel, improving the performance of small transfers. Diagram here has 4 disks. In disk 1 we have blocks A0, B0, C0, D0. Disk 2 we have blocks A1, B1, C1, D1. In disk 3 we have blocks A2, B2, C2, D2. In disk 4 we have blocks A3, B3, C3, D3. In disk 5 we have paired blocks AP, which includes A0, A1, A2, A3. We have BP, which includes B0, B1, B2, B3, CP, which includes, we have CP, which includes C0, C1, C2, C3, and last we have DP, which includes D0, D1, D2, and D3. Advantages of RAID 4. It's very high, it has very high read data transaction rate, it has low ratio of ECC parity disks to data disks means higher efficiency, high aggregate read transfer rate. Disadvantages of RAID 4. Quite complex controller design, worst write transaction rate and write aggregate transfer rate, difficult and inefficient data rebuild in the event of disk failure, block read transfer rate equals to that of a single disk. Now, we are moving to level RAID 5. RAID 5 consists of block level strapping with distributed parity. RAID 5 is the most common secure RAID level. It requires at least 3 drives, but can work up to 16 drives. Data blocks are strapped across drives, and on one drive a parity checksum of all the block data is written. The parity data are not written to fixed drive, they are spread across all drives. Upon failure of a single drive, subsequent reads can be calculated from distributed parity such that no data is lost. Extra cache memory can be used on these controllers to improve the write performance. It has a better read performance and large write performance. Reads can outperform sleds and RAID 0. It is most versatile RAID level. Diagram has 4 disks. In each disk we have block and parities. In disk 1 we have blocks A1, B1, C1, and DP. In disk 2 we have blocks A2, B2, CP, D1. In disk 3 we have blocks A3, BP, C2, and D2. In disk 4 we have blocks AP, B3, C3, and D3. Advantages of RAID 5. Disk failure has a medium impact on throughput. Advantages of RAID 5. Highest read data transaction rate, medium write data transaction rate. High efficiency means low ratio of ECC parity disks to data disks, good aggregate transfer rate. If a drive fails, you still have access to all data, even while the failed drive is being replaced and the storage controller rebuilds data on the new drive. Required applications are file and application server, database server, web, email, and news servers, internet servers. Disadvantages of RAID 5. Disk failure has a medium impact on throughput. Most complex controller design. If one of the disks in array using 4 TB disks fails and is replaced, restoring the data, we are talking about the rebuild time, may take a day or longer, depending on the load on the array and the speed of the controller. If another disk goes bad during that time, data are lost forever. Difficult to rebuild in the event of a disk failure as compared to RAID 1, as we have talked just before. Individual block data transfer rate, same as a single disk. And finally, we have our last level, RAID 6. RAID 6 consists of block level strapping with double distributed parity. RAID 6 is essentially an extension of RAID level 5, which allows for additional fault tolerance by using a second independent distributed parity scheme, which is called dual parity. Data is trapped on a block level across a set of drives, just like in RAID 5, and the second set of parity is calculated and written across all the drives. RAID 6 provides for an extreme high data fault tolerance and can sustain multiple simultaneous drive fails. It requires at least 4 drives and can withstand 2 drives dying simultaneously. Required applications are file and application servers, database servers, web and email servers, and internet servers. Diagram has 5 disks. In each disk we have blocks and independent parities P and Q. In disk 1 we have blocks A1, B1, C1, and DP. In disk 2 we have blocks A2, B2, CP, DQ. In disk 3 we have blocks A3, BP, CQ, and D1. In disk 4 we have blocks AP, BP, C2, D2. And in disk 5 we have blocks AQ, B3, C3, and D3. Advantages of RAID 6. Like with RAID 5, read data transactions are very fast. If 2 drives fail, you still have access to all data, even while the failed drives are being replaced, so RAID 6 is more secure than RAID 5. RAID 6 protects against multiple bad block failures while non-degrading. RAID 6 protects against a single bad block failure while operating in a degraded mode. It's a perfect solution for mission-critical applications. Disadvantages of RAID 6. This is a complex technology. Rebuilding an array in which one drive failed can take a long time. Controller overhead, compute parity address is extremely high. Very poor write performance. It requires N+2 drives to implement because of two-dimensional parity scheme. Here are the documents and slides I have used. Special thanks to Ijaz Saigan. The slides are based on his lectures. So thank you all for listening to me. Have a nice day.